To understand the central limit theorem, we need to go back a section and remind ourselves of what a sampling distribution of sample means is. So let's take a look at the population that contains the weight of all college female students measured in pounds. So I want you to imagine that inside this circle, just think of it as like this giant fishbowl where I have collected data from every single college female students and I ask them, how much do you weigh? And then each X that I collect represents a female's weight. Okay, so what I have on the left here, I can take all of that data that I collect from the entire population and I can plot it. So some X's are going to be repeating, meaning some college students might have the same weight. Some college students may weigh more. Some college students may weigh less, and I'm talking about female college students. But we know that the weight of college female students is normally distributed, so it's going to be bell-shaped, where at the center, if I average all of these X's, so the weight of every individual college female student, um, let's say that I find out that the average weight for the entire population is 140 pounds with a standard deviation of 26.4 pounds. Okay. All right. So what I have on the left here is this distribution of what we call individual values, where each X is the individual weight of an individual college female student, okay? And on average, college female students weigh about 140 pounds with a standard deviation of 26.4 pounds. Okay, now when we take a look at sampling distributions of sample means, what we're saying conceptually is we're saying this. We're saying, what if I do a study where I take a random sample of, let's say I take a random sample of just 4 college female student weights. Okay, so I'm going to close my eyes and randomly select, 4 weights. Let's say it's those 4 weights. Then those 4 specific values, I can calculate the average or the mean of those 4 values. And the mean or the average of that number is going to just depend on which 4 x's I randomly choose. Okay. So what I am going to do is I'm going to keep repeating this process. So I'm going to keep randomly selecting 4 more female weights, so same sample size, and then calculate the average of those 4 weights. Now, the average or the X bar value, okay, could be the same the second time I repeat this study, or it could be a number that's completely different. So again, we keep repeating this process over and over again, saying, okay, what if I randomly select 4 more adult females and calculate the average weight? What is that going to be? So the idea is that we repeat this process of selecting many, many, many samples from the population, all of the same size, and then calculate the individual sample mean values for our sample. It turns out that if I could do this, I'm going to collect lots and lots and lots of X bar values, so lots of different X bar values. And then what I can do is I can create another distribution. But this distribution, instead of being a distribution of individual X's, this is going to be a distribution of all of these X bar values. And what we learn in the previous section regarding sampling distribution for these sample mean values is we learned that this distribution, it also turns out that it is bell-shaped. It's also normally distributed. And there is a very interesting property. Okay, so again, let's say that, I do this study, maybe it's this X bar value, and I do this study and it turns out it's this X bar value, and I do this study and it's this X bar value. So again, I keep repeating the process and I try to find out, what are all the possible random samples of size 4 can I get? What are their individual X bar values? And I plot it on this distribution. So the central limit theorem, so now let's talk about the central limit theorem. The central limit theorem tells us that there's something really interesting about this sampling distribution for sample means. It turns out that if I take a look at this distribution on the right, okay, which is no longer a distribution of individual x values, it's a distribution of x bar values, which is the average weight, every time I randomly select 4 adult females and average their weight. It turns out that if I take the average of all of these averages, okay, so when I take the average of all of these averages, the notation that we use is this, mu sub x bar. The central limit theorem tells us that it turns out that when I average up all these individual x bars, it actually targets the population standard deviation. So it starts approaching the actual mean value of the single value distribution. The other thing that the central limit theorem tells us is it says when I calculate the standard deviation of this sampling distribution of sample mean values, so this sampling distribution of x bar values, it actually equals the population standard deviation divided by the square root of 1. So this is what you need to know about the central limit theorem, that we have this unique distribution of x bar values, and it turns out that the average or the mean of this distribution is equal to the population mean value, and the standard deviation of this distribution is the population standard deviation divided by the square root of 1. So the reason why this concept is really important is because if you think about what's happening in the real world, every time that you have a research question, I want to know, do college freshman students actually gain 15 pounds or not? I don't know the answer to that question unless I could survey every single college freshman student in, let's say, the United States. But I don't have time or money or the resources to survey every single college student. What I can do is I can do a study where maybe I just take a random sample of, let's say, 125 college students. And then from my study, so I'm doing it on the bottom here, and let's say from my study, right, the average weight gain of those 125 students is only 3 pounds with a standard deviation of like 2.6 pounds, right? Then the question becomes, how do I know that my study, right, is representative of what's happening at the population level? Because I only have time to do one study. And this could apply to any research question that you have. Maybe you only have time to do one clinical trial. You only have enough time to do one poll, one survey. And so what we do in statistics is we ask ourselves, I'm going to use yellow here, when I do my one study, and I take a look at my results, where does my result fall on this distribution? Does it fall at the center, which is occurring at a high frequency? So, am I getting results that's highly expected? All right, something that we expect to happen, or am I getting a result that falls in the tail? Let's say it's this X bar here, where it has a very low probability of occurring. And so, in statistics, we look to see where are the results of our study falls on this sampling distribution. And then based on the likelihood or the probability of it occurring, we can determine if our results are significant or not. And so in healthcare, that's where you hear terms like, oh, the results of this clinical trial is statistically significant. Okay. All right. I'm going to make another video to show you how we can apply this to some real world problems.